Created by MindSticks Foundation Trust. Welcome to today's Explainer, students. I am very happy to guide you through a truly fascinating topic in physics today as we explore exactly how different materials interact with heat. Let's dive right in, shall we?
Here is our quick agenda for today. First, we'll look at specific heat capacity. Second, the principle of heat exchange. Third, using the calorimeter. And fourth, we'll practice solving heat problems together.
Section 1. Specific heat capacity.
Imagine we take three solid spheres. We have one iron, one copper, and one lead. Now they all have the exact same mass. We place them in boiling water until they all reach a uniform temperature of 100 degrees Celsius, and then we immediately move them onto a thick slab of solid wax. Now pay close attention to what happens here. The iron sphere melts the deepest into the wax. Copper goes to an intermediate depth, and the lead sphere sinks the least. So why does this happen? Well, even though they were all at 100 degrees initially, the iron sphere actually absorbed more heat energy from the boiling water. And because it held more heat, it had more heat to transfer to melt the wax.
This brings us to a crucial formal definition. The specific property that determines the amount of heat absorbed by each of those spheres is called its specific heat capacity. Simply put, it's the amount of heat energy required to raise the temperature of a unit mass of an object by exactly 1 degree Celsius. In physics, we denote this with the lowercase letter c. Now for your units, in the SI system, we measure this in joules per kilogram degree Celsius. Meanwhile, the CGS unit is calories per gram degree Celsius.
Here's the actual data proving what we just saw in the wax. Iron's specific heat is 0.110 and copper is 0.095. So iron's higher value perfectly explains why it melted more wax. But I want you to pay special attention to water at the very top of this chart, sitting at 1.0. It is nearly 10 times higher than iron. This is exactly why a metal pan burns your hand almost instantly on the stove, but the water inside that same pan seems to take forever to boil. Water takes a lot of energy to heat up.
So the crucial point is how we actually calculate this heat energy mathematically. Here is your foundational formula. Heat energy, whether absorbed or lost, equals m multiplied by c multiplied by delta T. Let me methodically break that down for you. M is simply the mass of the object. C is the specific heat capacity we just defined. And delta T is the change in temperature. That could be an increase if the heat is absorbed or a decrease if the heat is lost. Please keep this formula fresh in your mind. You're absolutely going to need it for our calculations later.
Section 2. The principle of heat exchange.
If heat is exchanged between a hot object and a cold object, what exactly happens? Obviously, the cold object gains energy and its temperature rises, while the hot object loses energy and its temperature falls. This beautifully illustrates what happens in an isolated system. Imagine a heat-resistant box. This system is completely isolated from the outside environment. This means no heat energy can flow in from the outside and absolutely no heat can escape from the inside. The exchange of energy is strictly taking place only between the hot object and the cold object inside this box.
Because this system is perfectly isolated, we arrive at a very simple yet incredibly powerful logical rule. Read this foundational statement with me. Heat energy lost by the hot object equals heat energy gained by the cold object. This is known as the principle of heat exchange. Just let the pure logic of that rule sink in for a moment. Energy is perfectly conserved here. It simply transfers from the hotter body to the colder body until they both reach the exact same final temperature.
Moving on to Section 3. Using the calorimeter.
So, when you put a hot solid object into the water inside a laboratory calorimeter, heat exchange begins immediately. The solid object gives away heat, and both the water and the inner vessel of the calorimeter itself absorb that heat. Let's break down this complex exchange into 3 manageable steps so you aren't overwhelmed by the algebra. Step 1, we calculate the heat lost by the hot solid object, and we will call this Q. Step 2, we calculate the heat gained by the water, and we call that Q1. And step 3, we calculate the heat gained by the calorimeter vessel, calling it Q2.
By applying our principle of heat exchange, we know that the total heat lost must be exactly equal to the total heat gained. Combining those 3 distinct steps gives us our final mixing equation used in the laboratory. Q equals Q2 plus Q1. Or, explained in words, the heat lost by the hot solid object equals the heat gained by the calorimeter plus the heat gained by the water. Using this exact equation, if the specific heat of the water and the calorimeter are known, we can easily calculate the specific heat of any unknown solid object.
Section 4. Solving heat problems. Let's look at some practical examples.
Let's look at example 1. How much heat energy is necessary to raise the temperature of 5 kilograms of water from 20 degrees Celsius up to 100 degrees Celsius? The very first step with any word problem is to carefully extract our given data. Our mass, m, is 5 kilograms. The specific heat capacity of water, C, is 1 kilocalorie per kilogram degrees Celsius. And our change in temperature, our delta T, is 100 minus 20, which gives us 80 degrees Celsius.
Now we systematically apply our method. Step 1. Write down the foundational formula. Energy equals m multiplied by C multiplied by delta T. Step 2. Substitute the given values into the formula. So we are going to multiply 5 by 1 by 80. Step 3. We do the simple multiplication to arrive at our result. 5 times 80 is 400. Therefore, the total heat energy necessary is 400 kilocalories. It's quite straightforward when you follow the steps methodically, isn't it?
All right, let's tackle a slightly more complex scenario. Example 2 utilizes the mixing method in the calorimeter setup we learned about just a few minutes ago. Imagine a copper sphere with a mass of 100 grams heated to 100 degrees Celsius and then dropped into a calorimeter containing water. Our goal here is to find the maximum final temperature that the water will reach.
Because there are multiple parts to this system, we really must carefully lay out all our variables first. Let's start with the hot object, the copper ball. Its mass is 100 grams, and its specific heat is 0.1. Next, for the cold objects that will be gaining the heat, we have water with a mass of 195 grams, and the calorimeter itself with a mass of 50 grams. Now, the initial temperature of both the water and the calorimeter is 20 degrees Celsius.
Let me just remind you of the primary equation we'll use to balance this heat exchange. To find the final mixture temperature, which we will simply call T, we state that the heat lost by the copper ball, Q, must be exactly equal to the heat gained by the water, Q1, plus the heat gained by the calorimeter, Q2.
Let's perform the algebraic substitution. We plug in the mass, specific heat, and temperature change for each item. For the copper ball losing heat, its temperature decreases down to T, so the change is 100 minus T. For the water and calorimeter gaining heat, they warm up to T, so the change is T minus 20. Setting these sides equal gives us 100 times 0.1 times the bracket 100 minus T equal to the heat gained expressions on the right side. When we group our T terms together, it yields 210 T equals 5,000. Dividing that gives our final answer, T equals 23.8 degrees Celsius.
We have covered some incredibly important ground today, students. Your final assignment is to answer the questions you see on the screen. Define specific heat capacity and explain how you would prove it experimentally using our wax block and metal spheres from earlier. But beyond the classroom, I want to leave you with this final thought. The next time you marvel at a cool ocean breeze on a scorching summer day, remember the lesson of the calorimeter. It's actually the very high specific heat of our planet's oceans absorbing that incredible solar energy, quietly protecting us through the invisible mathematical elegance of physics. Thank you so much for learning with me today.